All right, we are on chapter 8, section 3. And so we're going to work on writing chemical equations for solution formation. And so in order to do that, we have to kind of understand that there are different kinds of ways that different substances dissolve. So ionic compounds, so for example, NaCl, right? Those we've talked about. We've said, okay, what happens when you have NaCl and you put it inside of water? Well, when you put it inside of water, what you're going to end up forming, right? It's a solid. And so we're going to put a little arrow. And what happens? We're going to put water under that arrow so we can say, you know, we're dissolving it in what solvent, and that solvent is water. What's going to happen to it? Well, we know that we're going to get sodium ions that are going to be positively charged, and we're going to have chlorine ions that are going to be negatively charged. And so for this reason, we say that ionic compounds that dissolve in water are called strong electrolytes. And an electrolyte, I know you've probably heard this before when you buy like Gatorade or Powerade or whatever, it's got essential electrolytes, you know, all that kind of stuff. What is that telling you? It's telling you got some salt in there. And they make you spend a lot of money on it. So we call them strong electrolytes because they can propagate an electrical signal, right? So anything that has ions inside of it can propagate electricity. So if you've ever seen on like a blow dryer, right? You've seen a little tag, do not drop in the water, you will be electrocuted, right? Why? Why? Because those ions can basically complete a circuit, an electronic circuit. And so electricity will flow through the ions that are inside of the water. So that's why, like, if you're in the pool and it's lightning, it's everybody out of the pool. Because if lightning strikes the water, right, everybody who's in the pool will get electrocuted. So that's why everybody gets out the pool when electricity strikes. So that's ionic compounds. Soluble covalent compounds do not ionize. So if you have sugar, right? Your sugar is C6H12O6, right? What happens when you put that into water? It's still a solid. What happens? Well, I get C6H12O6. It didn't change. It's just now surrounded by water, so we call it aqueous. But did we make any ions? No, we have no ions. We have no charged particles. And so they don't conduct electricity. So if all you had was sugar inside of the pool, then you would be fine. It wouldn't propagate an electrical signal. And then there are some compounds that partially ionize. And if they partially ionize, we call them weak electrolytes. And so the example that they have here for a covalent compound is CH3 COOH. And when this is a solid and we dissolve it in water, I don't have enough room, right? What can happen is that you get CH3COO minus, and then that hydrogen pops off and it becomes a plus. And so we say these are both aqueous because they're in water, but look, we have a charge, but it doesn't happen all the way. And so instead of writing a single arrow, what we write is we say, a little bit of it does, but a lot of it likes to stay in the solid form. So we give it that equilibrium arrow. And so you can see the illustration of that here. A strong electrolyte would be like magnesium chloride, MgCl2. So you have magnesium ions and chloride ions, and the ions can actually propagate that electrical signal, complete the circuit, and then it lights up a light on top of the little device. So you just dissolve some salt in water and you can see the electricity go through the solution. A non-electrolyte like sugar, right, will get covered in water particles, but it won't become an ion. So it's a non-electrolyte. And then our last one is a weak electrolyte. And so you see that sometimes the hydrogen ion will come off, but a lot of times the hydrogen ion is still attached to our substance, and so it's not charged. So it doesn't light up the light very much. I don't know why it's red. I don't know. Usually it's just dim. But so how do we write these equations? Well, I just kind of showed you this. Magnesium chloride is an example of the strong electrolyte that they did. And so if you wrote the formula for MgCl2, so if you went on the periodic table and you went and looked up magnesium, You would see magnesium is in the second column. That second column tells us that we have a charge of +2. You go look for chlorine. Chlorine is in column 17 or 7A, so it's -1. And so in order to write the formula, right, we do our little crossover and we get Mg1, but we don't write the 1, Cl2. Okay, so that's how we got the formula for magnesium chloride. Now, it is a strong electrolyte because when we put it in water, we get our ions. So our ions are Mg2 plus aqueous plus 2Cl minus aqueous. I don't know how they forgot that. Now, you can find the charges just by going to the periodic table. But what you have to be careful of is you have to make sure that you balance these equations. So if we look on this side, right, we have 2 chlorine atoms because it has a little subscript 2, and we have 1 magnesium. Well, over here I have 1 magnesium, but I have to put this 2 as a coefficient in order to get 2 chlorine atoms on the product side. You can only add coefficients. You may not add subscripts. Be very careful about that. Okay, so if you were to say this formula, you would say solid magnesium chloride dissolves in water to yield magnesium and chloride ions. Okay, so the number of magnesium and chloride ions that are formed as products is the same number as what was in the reactants, right? So in order to make MgCl2, we had to have 2 chlorines for every 1 magnesium. Well, the same thing's true in the product, right? That's our law of conservation of matter. And the other thing is that the left-hand side of the equation has no charge, right? You can see that there's no charge because the charges in magnesium chloride balance out. Well, the same thing should be true about our products. So we have Mg plus 2, that's a charge of +2, right? +2. Then we have chlorine, which is a charge of -1, but we put our coefficient of 2. So we have a +2, and then 2 times -1 is -2. So you add those up and you get 0. So both sides of the equation, this side is 0 as well because we have 1 magnesium, which is a +2, and then we have 2 chlorines, which is 2 times -1. So it's a 0, right? So your products and your reactants must equal to 0. Okay. All right. Oh, and then we just did this. Okay. So the other thing to note is that when we write these reactions for strong electrolytes, that arrow is a single shot. It's only going one way. And so it's telling us that this reaction is irreversible. So in order to reverse the reaction, you'd have to do something. You could evaporate it, yes, and you would get solid back, but you would actually have to do something. If you just dissolved it and left it, nothing would happen, right? It's irreversible. So for ionic compounds, the reactant is usually going to be a solid. So that's where we put the little S right here. That's what the solid's standing for. And then in the products, we're always going to have aqueous because they're dissolved in water, right? So substances such as solvents that are not actually involved in balancing this equation, we don't put them as reactants or products. We just put them under the arrow so that we know that this reaction was done in water, but water doesn't actually participate in balancing this equation. Non-electrolytes, right? Non-electrolytes, these are our polar covalent compounds like sugar, right? We put a solid, we put it in water, and what do we get out? We get out a dissolved substance. So it is aqueous, but it's not ionized. There are no charges. And so they don't, by definition, they don't disassociate. Disassociate means kind of like break up into those ions. And so there's none of that happening. And so the only difference between the reactant and the product is the phase. So in the reactants, we're solid, in the products, we're aqueous. So that's how we indicate it in our reaction. And then you can't go backwards without doing something. And so you leave that straight shot arrow. So the last one are weak electrolytes. There are two really common functional groups that contain a form that can gain or lose a hydrogen. And those are the carboxylic acids. When carboxylic acid loses this hydrogen, it turns into the carboxylate, and the carboxylate is the charged form, so it carries a -1 charge. And then the other one is an amine. amine, excuse me, an amine. And when we have our amine, what we can do is the reverse. We can actually add a hydrogen. So instead of having this lone pair, right, we're going to actually add this hydrogen in. Well, that hydrogen is going to give it a positive charge. So our charge form is positive, so we call it protonated. It has that extra hydrogen, and so it has a positive charge. So a lot of times what you'll see, the carboxylic acid, you'll see it listed as COOH and then COO minus. They just don't show the double bond. But be careful that you know that that's a carbonyl. One of these is a carbonyl. So this oxygen, right, is actually, if I can move it, is actually up here, and it has a double bond. And then you have a bond to that oxygen. That oxygen's bonded to the hydrogen, and then you have an R group, right? But we just abbreviate it COOH. That's what we do. Okay. So our carboxylate, right, has our really, really polar hydroxyl, right? We've talked about that. That can participate in hydrogen bonding. And so when that disassociates and it forms our carboxylate ions, right, we end up with a negative charge here, and we end up with a positive charge on our hydrogen, on our free hydrogen. So we call those hydrogen ions. So as this starts to happen, sometimes you're going to have the reaction go in the reverse direction, where some of those hydrogens are now going to jump back onto this oxygen, and you're going to form back into our carboxylic acid form, right? So this is our carboxylic acid. This is our carboxylate form. And so the way that we show that is then we show a double-headed arrow. So this double-headed arrow tells you that the reaction is going in both directions. And we get to an equilibrium where the total amount of these charged things being formed is equal to the number of the carboxylic acid being formed, right? And so what's interesting to note, though, is that our charges are still balanced, right? So if you look on the left side, everything's neutral. You look on the right side, you have one negative and one positive. Well, what's a negative and a positive? Zero. So our charges are balanced. And when you look at the phases, when you look at the states of matter, right, the weak electrolyte beforehand can be, this one beforehand, it can be a solid, a liquid, or a gas. But then it always is going to turn into aqueous because it's in water. All right, so there are great examples of these things going on in our bodies. So especially in our blood and all kinds of other bodily fluids where we have electrolytes as dissolved ions. So the amount of a dissolved ion found inside a fluid can be expressed by the unit equivalent. So depending on how many, what the charge is, you get an overall number of charges inside the solution. And it's related to the charge of the ion and the number of moles of the ion present. So you have to take into account both of them. So let's look, for example, at sodium. Sodium carries a charge of +1. Because sodium is +1, and we know it's in column 1, so that's how we know it's a +1. We know that there is for every 1 mole of sodium ion, we have 1 mole of basically a positive charge. And we call that 1 equivalent sodium ion, right? Now, calcium, on the other hand, calcium is carrying a 2+ charge. It's in column 2. So if we have 1 mole of calcium +2, what is that giving us an overall charge of? It's giving us an overall charge, right? For 1 mole of calcium, we're going to have 2 moles of charge because each atom is carrying a +2 charge instead of a +1 charge. Okay, so the equivalent for calcium is 2 equivalents of charge for every 1 mole of calcium. And so you have to be very careful that you can write these conversion factors because yes, we're going to have to use them in dimensional analysis. Okay, chlorine, an example, chlorine. Chlorine's a -1, but it's still only a 1. So when you write your equivalence dimensional analysis, right? You're going to say for every 1 equivalence of a chlorine charge, you have 1 mole of a chlorine charge. SO4 is a polyatomic ion, so you can go find it on the polyatomic ion chart. It has a charge of -2. So for every 1 mole of my substance that's carrying a -2 charge, I have 2 equivalents of charge. So the number of equivalents present per mole of an ion equals the charge on the ion, right? So we'll use those in some examples. In our blood plasma, right, we have lots of electrolytes. And so it's very, very important that the concentration of these electrolytes remains consistent. And so this is highly monitored, and we typically represent ions in bodily fluids in milli equivalents per liter of solution. So milli just meaning thousandth, right? And so like you're going from milliliter to liter, you're going from milli equivalent to equivalent, okay? And we'll do some dimensional analysis with that. And so depending on the different cations and anions, these are the common concentrations inside of different bodily fluids, right? And so you have to think about, we need to balance the number of positive and negative charges present so that when we dissolve our ionic compounds, we have that net negative charge. And so our blood plasma is going to have a total electrolyte concentration of 150 milli equivalents per liter, because we have 150 total of our positive, cations are positive, and we have 150 milli equivalents per liter of negative ions. And so if we look right in our blood plasma, we have an equal number of positive ions and an equal number, it's not of ions, I shouldn't say that. We have an equal number of plus charges as we do negative charges. And so they balance out so that our blood actually ends up being neutral. Okay, so if you are going to give someone fluids or some kind of treatment, right, you have to be very, very careful that you provide the correct amount of ions in those solutions. So if you need to give someone a bag of saline, normal saline, right, you have to be very careful that you put the correct milli equivalents per liter of ions. And so you have to put in a specific amount. If you have a patient maybe who has more than just hasn't had enough to drink, right? What if it's malnutrition and dehydration? Well, you want to give them, in addition to an ion, right? In this case, we'll give potassium chloride. We're also going to give dextrose, which is a sugar. And so you have to make sure that you're giving the right concentration of ions and the right concentration of sugar. A lot of times, if you have a lot of fluid loss and you really need to be careful that maybe their blood pH is off, right? Then you're going to give them a slightly different solution, and it's going to have some ions in it, but it also has lactate in it. So there are all kinds of different things that you need to be very, very careful that you give them the correct ratio of negative to positive ions so that you treat them correctly and you don't end up killing them, right? All right, so the amount of solute dissolved inside of a solution determines its concentration. And this is a lot of times how we represent how much of something we're giving to a person or a patient, right? So our concentration of our solution typically gets expressed in amount of solute over amount of solution. So remember, solution is solute plus solvent, right? That's the two things together. And so just be careful that you make sure and you add that solute and solvent to get your solution. So it's like the part over the whole. Sometimes the other way that we express how much of something we're going to give to a patient. Oh, and I'm jumping around. I went too far. All right, I'm stopping. I'm going to 8.3. I was just on a roll, y'all. Hold on. Okay, so we're working on our in class problems, right? All right, so predict if the following IV electrolytes will fully dissociate, partially dissociate, or not dissociate when placed in solution. Potassium chloride, a strong electrolyte. If it's a strong electrolyte, by definition, what's it going to do? It is going to fully dissociate. So this is fully dissociate. Sodium lactate, a weak electrolyte. So what is a weak electrolyte? It's one that undergoes that equilibrium where it's creating the ion and then going back to the neutral form, creating the ion, going back to the neutral form, right? So that's a partially dissociated substance. All right, dextrose, D-glucose, right? It's a non-electrolyte. We're not going to make any ions. So is it going to dissociate? Is anything going to come apart or off or anything like that? No. So this is not dissociating, or will not dissociate, however you want to say. All right. Provide a balanced chemical equation for the hydration of each compound in problem 8.13. And look at that, I gave it to you. Isn't that so nice? All right, so what do we have in A? We have potassium chloride. So we have KCl, and it's a solid. It's a strong electrolyte. So what we're going to do is we're going to put that solid arrow, and we're going to put water, because that's what we're dissolving in. Now, what's going to happen? You can go to the periodic table and you can go find your charges. So find potassium and find chlorine. What's the charge on each of them? You should find that it's a positive for potassium. So that makes it a +1. And then we say we dissolved it in water. So that's going to be aqueous. And then we have chlorine. Chlorine's in column 7 or 7A or 17. So chlorine's a negative, and that is aqueous. Not a G, a Q, aqueous, right? So this is our reaction for a fully dissociated strong electrolyte. B, sodium lactate. So we have NaC3H5O3. This is a weak electrolyte. When you say weak, you should think about doing that double-headed arrow, right? Because weak means that it forms a few ions, but then they go back and then they go back, right? Okay. So then you have what comes off is our sodium right here. This becomes an ion, and we know we can go and look and find this on a polyatomic ion chart. So it would be good to be able to go and use your polyatomic ion table that's in your exam resources, also in your book. Okay, so sodium's in group 1, so it forms a +1. And then our C3H5O3 forms a negative ion. You'd find that in polyatomic ion chart, and it is aqueous. Okay. All right, C. C6, it's our dextrose, H12O6. That is a solid. And what's going to happen? It's a non-electrolyte, but it has hydrogens bound to oxygens, and so it's going to interact with water through hydrogen bonding. So it's going to be soluble. So it's going to dissolve, but it is not going to form ions. So that's C6H12O6, and this is aqueous. Okay, so it did not form ions, therefore it isn't a non-electrolyte. All right, for the following compounds, write a balanced equation for their hydration in water. All right, so we start with A, CaCl2. This is going to be a solid, calcium chloride. It's an ionic solid. Put it into water, and what's going to happen? Go on the periodic table. Go find calcium. If you need to pause it at any point, you can always pause it. Ca2+, and it's aqueous because it's in water, plus Cl-, which is aqueous because it's in water. Now, the big thing that you have to worry about is, are my equations balanced? And I didn't say that up here, but they are all balanced. Okay, they are all balanced. But this one, guess what, is not. If I look here, I have 1 calcium. Ooh, don't want to be on a race. I have 1 calcium, I have 1 calcium. Here I have 2 chlorines, and here I only have 1 chlorine. So I'm going to have to add a coefficient in order to balance that chemical equation. So now I have a balanced chemical equation. All right, B, I'm doing NaOH. Okay, and that's going to be a solid. I'm going to put it in water, and what's going to happen? Well, this is going to split up. And so I'm going to have sodium plus turning into an aqueous, and then OH minus will be aqueous. Okay, so that's polyatomic ion chart. All right, C, KBr. K is, go look on the periodic table. K should be in your column 1. So it's a +1. It's aqueous. Plus bromine. Bromine is in column 7. So it's -1, and that's aqueous. And we're balanced. So some of these are nice that you don't have to balance, and some of them you do. Okay, D, FeNO3, 3. So this is going to be a solid. Oh, y'all know what I did missed on the other one? Put your water. Okay, so what's going to happen is we're going to disassociate right here. Here's a polyatomic ion, and then the iron, you can go look on the periodic table. But the problem with iron is that it's a transition metal. So how are you going to know what charge iron is? Well, you're going to look here at the subscript, because you basically reverse and put your 3 up here and make it positive, because you know the cation's listed first, and then you really have a 1 here, and so that becomes a -1. So we have Fe3 plus, or +3, however you want to say that. It is aqueous, and then we are also going to have our product of NO3, and that's a minus, and that's aqueous. Are we balanced? We are not, right? We have 1 iron over here. Now you don't have to balance every single atom if you just kind of look at it as a big picture. So let me kind of erase everything that's going on over here. So much going on. Okay, so let me go put it back. I had NO3, 3. Okay, so what I can see is I have 3 of these polyatomic ions that are NO3, 3. This is what that means, because this subscript is outside of the parentheses. That's telling me that I have 3 of those NO3 polyatomic ions that are attached to the iron. So when they disassociate, I'm going to end up with 1 iron atom at the center, right? And then I had 3 polyatomic ions surrounding it, bound to it. Well, not well, in an ionic bond. And then when I dissolve it in water, those 3 ionic bonds are going to separate. And so I'm going to need to have 3 of those polyatomic ions. Okay, so be careful that you correctly balance. And it's true, you look, you have 3 nitrogens on both sides, and then you have 9 oxygens on both sides. Okay. All right, how many equivalents of K plus are present in a solution that contains 4.25 moles of K plus? Dimensional analysis. All right, so what do you start with? You start with 4.25 moles of K plus. All right, so what happens? Well, I need to remember that because my potassium carries a charge of +1, what do I have? I have 1 equivalent charge in K plus per 1 mole of K plus. So what does that tell me? I have 4.25 equivalent charges in my potassium. Okay. Let's try a slightly more challenging one, right? Okay, a sodium chloride intravenous IV fluid contains 154 milliequivalents of sodium per liter of solution. If a patient receives exactly 500 milliliters of the IV solution, how many moles of NA were given? So here's our goal. How many moles were given, right? What are we going to start with? We're going to start with our 154 milliequivalents of Na plus. All right, so let's see where we're going. What are we going to do? We want to, I'm sorry, and I didn't say per liter, per 1 liter of solution. Okay, so what do we want to do? Well, let's take care of what's on the top first, our milliequivalents. Well, if it's milli, that means I have 1,000 milliequivalents in 1 equivalent. Okay, so that's how I get rid of my milli, and I'm left with equivalents. All right, so I know in 1 equivalent Na plus per 1 mole of Na plus, because Na has a charge of +1. So that tells me that my coefficient right there is going to be a 1. That's how I know that. Okay, now I want to know if a patient receives exactly 500 milliliters. Well, I'm in liters, so I need to convert from 1 liter to milliliters, right? But that's per 1,000 milliliters, and that's not what I want. I want it to be for 500 milliliters. So you could just multiply by 500 and you should get 0.0770 moles of Na plus. Okay. All right, that is the end. You'll have a great rest of your day.